You about ready to roll?
Yep, you're good.
Well, thanks, that was super
You ready?
helpful.
What's that? Mira does all those things.
Let's see, is the mic on? Okay.
No? Oh, try again, I couldn't hear you.
Yeah, well, I can talk more than loudly enough for everybody to be able to hear me, but I wanted to see. How are we now?
Yeah,
There
there
we
you
go,
go.
all right. All right, yeah, come on up. So, our speaker today is Alexander Goodson. I think he likes to go by Alex.
Yes, that's right.
And he's originally from Waco, Texas. 2020 graduate from Baylor University. Very interesting double major, geology and German. So completed his master's in geology at the University of Arkansas, go Hogs. I'm living in Little Rock for the last 11 years. And his interest in geology came about as a result of his interest in the outdoors and mountain biking, a lot of outdoor activities and everything. And you know, he was smarter than I was. I love the outdoors too, but I ended up with an office job. So, he really decided that science and the outdoors was something that he wanted to combine. And so he moved into geology. And he had an opportunity in Arkansas with a company called Mining to investigate the Mona Lisa mine in Arkansas. And he looked at both the historical and cultural aspects of it, as well as obviously the geologic aspects of it. And now is working as a research associate at GIA, and is the specialist, the collection specialist for Carlsbad colored stones. So I had a great opportunity to interview him myself. If any of y'all saw the video prior to the conference and everything, and I'm really interested in hearing what he's got to say, because having lived in Arkansas for 11 years, I never thought there was any turquoise in Arkansas.
All right, well, hello everyone, and thanks Craig for the introduction, and thanks to Jacob and Joe Dan Lowry for allowing me to be here and talk about some of my research today. And I'm going to be talking about the Mona Lisa mine, which is an American turquoise locality, and what makes this location special is that it's located in Arkansas, which is not one of the states that we typically think of as a traditional turquoise producer. And so the beads that you see on the screen here are from the Mona Lisa mine, and all the turquoise that will be shown in pictures in this slide of this presentation are from the Mona Lisa. These beads were photographed by Robert Weldon of the GIA library. So thanks for the introduction, Craig, about my background and how I kind of got into geology and then into turquoise, just because this opportunity opened up at the University of Arkansas to work both with the mining company as well as with the university to get a better understanding of this mine. So that was really neat. And I just want to go through an outline of what I'll talk about today. I'll start with kind of the purpose of my research, what inspired my research into the mine, and then I'll also talk about some background of the location, including the history and the geology of the site, which is kind of unique compared to some other turquoise localities. Then I'll get into the different methods that I used and the results from those methods for this study, which included going out into the field as much as I could, going to the mine itself, as well as then taking samples from the field back to the lab and studying their mineralogy and geochemistry. And then I'll talk about what the implications or conclusions that we have from the study are, and also give a brief summary of kind of what the mine-to-market process looks like from the Mona Lisa mine today. But I do want to start by recognizing the research team that helped me complete this project at the University of Arkansas. Dr. Tom Paradise, they all came from a variety of backgrounds, so I was able to tackle the problem in a variety of ways. And so Dr. Tom Paradise is worked as a jewelry appraiser for years. He also worked in mining for some time. He's probably best known for being on documentaries about the Petra Jordan Archaeological Site, so he's been on Nova, National Geographic, Discovery Channel, probably what he's best known for. And then Dr. Adriana Potra joined my committee that was working on this research, and she teaches mineralogy and economic geology at the University of Arkansas. She actually worked at the Morenci site earlier in her career in mining, so she had some experience with a turquoise producing site as well. Her research really specializes in the precise measurements of isotopes in rocks. So I was able to take her knowledge and apply it to turquoise, which in a cool way. And finally, we have Dr. Greg Dumond, who is a tectonicist and structural geologist at the university. He also has incredible four-wheel driving skills, and we would not have made it to the mine alive as many times as we did without his skills getting up there even before the mine road was created. And thanks to his car, it's called Eleanor. Now in this picture, Adriana's in the red shirt there looking at some shale. Greg is in blue behind her. Tom's taking the picture. I'm probably in the trench somewhere digging around. And then the guy in gray in that picture is a rock hound who at this time he had actually paid a fee to the mine owners to come visit the site and pick through the tailings to see if he could collect his own rough material. So he was there at the same time that we were doing some field work. So the purpose of my research was really twofold. And the first question I wanted to answer was, does the Mona Lisa mine actually produce turquoise? And there is a lot of skepticism about this, especially from geologists in Arkansas. Some of the geologists who are really familiar with the area in general didn't think that this could actually be turquoise because there's no obvious copper source in the area. There's no big copper mine or anything like that. And in fact, planarite, which is a mineral that's similar to turquoise, in the turquoise group, is pretty common in that area and does not have copper. And so they assume, well, all this stuff that people are saying is turquoise, it's probably just planarite that's being marketed as turquoise. And so that was kind of an opinion I heard a lot from geologists in Arkansas about the study. So I wanted to figure out, with samples from the mine itself, whether we could tell if it is turquoise. And then if it is turquoise, well, why do we have turquoise forming here? Because we're in a completely different climate environment, different geologic environment to the mine to the southwest, or most of them. And again, the copper question comes up, because there's no economic copper mining that goes on in Arkansas. And the only copper-bearing minerals that are found in any abundance are typically found in northern Arkansas, in the Ozark Mountains, which is still far away from this site. So to have turquoise, there had to be some copper source to produce that turquoise. So I wanted to figure out why you could have turquoise at this location. So the mine does have an extended history, although it's not very well documented. Don't worry, you won't be tested on any of this information. In the 1920s, the site was first recognized during the search for precious metals in the Ouachita Mountains of Arkansas. So at this time, a lot of people were looking in that area, which is relatively remote, for gold, silver, and copper, and happened upon this weird location here, and that's according to Sinkankis. Now, in the 1950s, it first opened commercially as a phosphate mine, and they called it a phosphate rock mine. And basically, they were blasting this material to use the powder in phosphate for fertilizers. Now, it's unclear exactly whether they were blasting really low-grade material or if they were actually destroying some gem-quality turquoise at the same time. It first opened as a turquoise mine then in the 1970s under the Newton Company ownership, which was based in Denver, Colorado. And then it changed owners to some independent miners from the Dallas, Texas area who were kind of construction contractors who just wanted to get into mining in their free time to make some money. During this time that it was open as a turquoise mine, it went by various names depending on who owned it and how they wanted to market it. So it went by the McBride mine for a time, the Newton mine, the Little Porter Mountain mine, the Mona Lisa mine, I think also the Bluebird mine for maybe a few months. A noteworthy figure in the history of the Mona Lisa mine is Jack Wigley. and he discovered a massive turquoise nugget from this location in the early 1980s. It's about 250 pounds, and we'll see a picture of it a little bit later. But the reason that this guy's so important is because he actually describes his ownership of the mine in that time period in an article he wrote in Rock and Gem magazine, published in 2006. So it's kind of the only real account that we have of the site about what was going on during this time. He estimates that about 25 to 30,000 pounds of turquoise were mined from the time he was affiliated with the mine, which was 1978 to 1986. Now that number is interesting as well because there was a wilderness study done right next to the mine, and they included the mine as part of the mineral resources of that study, and they estimated that no more than 600 pounds had ever been mined from there. So if you think about the difference between less than 600 pounds versus 25 to 30,000 pounds, the truth, maybe it's somewhere in the middle, but it's difficult to tell who had the correct answer on that one. It shut down in 1986 basically because of heavy competition in the turquoise industry. Basically, they weren't able to compete with the southwestern sites, weren't able to raise the popularity enough. And so the mine was reclaimed then in the early 1990s and kind of just sat there, and people started to forget about it, or if they ever knew about it in the first place, until that claim was purchased by Avant Mining, who are the current owners, in 2017. They're quartz crystal mining company who kind of happened on some previous owners of the turquoise mine and were able to get that lease. They dug a test trench then in 2018, which produced about 1,000 pounds of turquoise in 1 week, and then they presented the 250-pound nugget, which they had bought from basically a warehouse. And they presented that at the Tucson Gem Show in 2018. So that was kind of the re-entrance of the Mona Lisa mine onto the market as potentially some weird turquoise source in Arkansas. So here are a couple pictures of some of those figures. So Jack Wigley is the guy on the, I guess on your left in that photograph, and here he's with one of his one of the other owners of the mine, and here they've actually constructed a model of the mountain where the turquoise is found, and they're advertising it, looking for some investment, and you see there are little bars of something resting in front of the mine, and those are actually bars of silver, which they claimed came from the mine, came from the Mona Lisa mine at the same time. Now, I can't say for sure that they didn't find the silver at the mine, but there's no evidence of any silver coming from anywhere in the Ouachitas, let alone bars of silver coming from the Mona Lisa mine itself. So I think they're probably just looking for some extra investment there. And then we have an advertisement for Arkansas turquoise. This was published in the Lapidary Journal in 1980. An advertisement for Mona Lisa turquoise. They started calling it that at this point, where they're selling untreated, hard, natural turquoise from Arkansas. So they are marketing it at this point as Arkansas turquoise. With the increasing competition, though, they realized that maybe to make money might be easier to sell something that people already knew about. And so a large amount of the material was also sold as kind of southwestern turquoise. And so it's really difficult to track both the production of the mine during that time period and also to track any of the material, because a lot of it was being sold as southwestern just so you didn't have to convince the customer that Arkansas turquoise was a thing and that you should buy it, instead just that you should buy it, since they already knew about southwestern turquoise. So here is that 250-pound turquoise nugget here. I think this on the screen is probably a little bigger than it actually is in real life. The dimensions are actually about 3 feet in the long direction by 1.5 feet by 1 foot. And it is marketed at their museum and gift shop as the largest American turquoise nugget ever discovered. And I figure there's probably no better place than here to see if people would agree or disagree with that statement and what people might think of that. That's how it's currently displayed in gift shop slash coffee shop slash museum at one of the Avant mining locations near Mount Ida, Arkansas, which is a really cool place to go for quartz crystals as well. And from Jack Wigley's, actually, his anecdote about discovering the nugget, he said that it was at least several hundred pounds bigger. He just didn't know how to get it out of the ground without breaking it. And so he busted off big pieces of it. But he claimed that it was a lot bigger, or it could have been a lot bigger. Obviously, it's unclear whether that was just, extra host rock or low quality material since it broke off so easily. So just to give an idea about where Arkansas is in relation to us, we're about the width of Texas from east to west away from where we are now. And if you've ever driven through Texas, you know that's a heck of a trip. And in Arkansas, we can kind of divide the state into a couple of different regions or provinces. So you have the Ozark Mountains in the north, where Fayetteville and Bentonville are. Then you have the Arkansas River Valley and the Ouachita Mountains south of that. And this mine is located in the western Arkansas Ouachita Mountains. And this is a geologic map here, just showing the overall geology of the state. But if you were to zoom in to this geologic map, what you'd find that's much different than a lot of places in the Southwest is that there are barely any igneous rocks exposed in Arkansas. In fact, the closest igneous exposure to the mine is the Murfreesboro lamprite, where you can actually go to mine diamonds. So there's no volcanic association as there is with many regions of the Southwest. So here are some images of the mine itself from a couple of different visits to the mine. And it is in a different climate and geologic setting than the mines are in the Southwest. So we actually are located in the Ouachita National Forest. We have these trees that are changing color at this point in November. A lot of the trees had fallen into the mine. The mining company hadn't been out there in several months at this time because of weather and COVID related things. And then they really cleared it out in April when I had gone back, and they had actually graded the mine road so it wasn't as precarious to make it up to the site in general, and also made some parking. In this picture, there's actually a bunch of people there, and this was the crystal collector, is a YouTuber who goes around to different sites, and he kind of made a deal with the mine owner that he would, he and some of his subscribers would pay a fee to come basically rock hound and pick through the tailings at the site. So that's what all these people were doing here at that time. So we saw a little bit of the host rock here exposed in the trench in that picture from April, and that white rock face on the mine. And that rock is actually novaculite, which is a high purity silicious rock. It's really similar to Cherts. Arkansas is actually the type locality for this type of rock. And it outcrops in the area in kind of east to west trending ridges. And one of these ridges is where the turquoise forms. So the turquoise is forming in Arkansas novaculite in this outcrop in the Ouachita Mountains. And if we look at the shape of the novaculite outcroppings in the Ouachita Mountains, it's a really weird pattern here. That's not how we expect rocks to be deposited. And that's because of how the Ouachita Mountains actually formed, and then those rocks were deformed. So the Ouachita Mountains formed roughly 350 million years ago. That's well before the dinosaurs. And what you basically had was the North American plate moving to the south, and the North American craton was moving towards the south. You had another microcontinent, or another smaller continent, called the Sabine terrain moving to the north, and they collided with each other. When they collided with each other, North America started to slide underneath this other microcontinent. And as North America slid underneath, the rocks that were on top, like the novaculite, started to get scraped off. And as they're scraped off, that compression continues to occur, and those rocks get all jumbled together and fractured and folded like crazy. And in the red circle there, you can see that area becomes uplifted. And so here we have this mountain range that formed because of the collision between North America and this microcontinent. And because we have all these fractures and folding in the area, it's easy for fluids to travel through the system. And because those fluids can travel easily through those rocks, we get huge deposits of quartz, we get phosphate mineralization, because the pathways are there for mineralizing fluids to move. So I approached the project by first trying to get out in the field as much as possible, both to map the topography of the area, the geology of the area, how the turquoise mineralizes, and also look at different structural features there, as well as to collect samples. And then once we collected those samples, we took them back to the lab for more in-depth analysis, which included X-ray diffraction, Raman spectroscopy, and looking at the geochemistry of the samples themselves. Included in that geochemistry, we looked at some lead and strontium isotope ratios, which can maybe tell us something about the geology of the site. And luckily, again, I was working with Dr. Adriana Potra, who works with lead isotope ratios in all different types of rocks. And so we had the facilities and expertise to conduct that study. So there's a picture of me with a stadia rod, like a 10-meter long rod, as we were mapping the topography of the site, because of the tree cover, basically, you couldn't get any aerial photographs. And so we had to map this site by hand so we'd have some sort of reference when we were looking at the different features. So we did that with this stadia rod, tape measures, walking back and forth, measuring a bunch of distances to figure out the topography or the relative elevation of this mining site. Now, obviously, since it's an active site, that changes quite often whenever they bring in heavy machinery and things like that. But this was a reference that I'll then try and overlay some of the other information on top of. Now, we also looked at the geology of the site itself and found that that mine trench, that main trench that's being mined, is located in the Arkansas novaculite formation. So that is the host rock in this area. Now, novaculite is also kind of famous in Arkansas because it's used as a whetstone or as a sharpening stone. So it's a popular tourist gift for people who are traveling through that area. But there's actually also another formation of rock, the Missouri Mountain Shale, which is exposed just to the south of that novaculite. And then on the southern side of the mountain, you get back into novaculite. So basically you have an older formation that's exposed just at the very top of this mountain and novaculite on either side. And where there's a contact between geologic units, so where you have the shale turning into novaculite, you also have a difference in how fluids will move through those different rocks. And so because of that difference in porosity or permeability, that could be another reason why turquoise, which forms in the trench in this area, will mineralize adjacent to the contact between the shale and the novaculite. All right, so let's just focus on the image here for now, and if anybody wants to get into the stereo nets in the discussion, I'd be happy to. But in this image, that's a close-up image of the wall rock. And what we see is it's not just some flat, clean wall of rock. Instead, it's all fractured like crazy. And to measure where those fluids are going to flow, and therefore where turquoise might mineralize, we wanted to measure, well, what orientations do those fractures have? And is there any order to how the rock is fractured? And so me and Dr. Dumond, we took our Brunton compasses and measured the orientation of more than 200 different fracture planes. And we found there were two dominant fracture directions. And those are circled here in red, and that's kind of meaningless on this slide, but if we then transpose those fracture directions onto our map of the mine, we can see that the dominant fracture directions are near vertical, and they cut across the trench. and they actually intersect at about 60 and 120 degree angles. So the majority of fractures are near vertical, cutting through the rock, and because of their angles representative to each other, we can actually determine how that area was deformed to cause those fractures. And in this case, we would have extension along the trench from extension east-west direction, basically, which was pulling the rocks apart, opening up these fractures that then mineralizing fluids could flow through and potentially precipitate turquoise. And now we can look at what the turquoise actually looks like in the rock itself. And we see some of the material is concentrating in near vertical patterns. Not all of it. You see some in horizontal directions, some kind of discrete areas. And it's not as simple as just measuring the orientation of the fractures, because this whole area has then been altered significantly. And so you get secondary fracturing and things like that. But this would identify how you originally got the fractures that allowed turquoise to form at the site. And we also tried to collect samples of varying grades and sizes from the mine while we were there. So that included kind of some digging into the wall rock when we could for the lower grade material, as well as looking for nuggets and things that were left in the tailings piles from previous mining at the site. We also were donated several samples by Avant Mining to help kind of encapsulate a range of material from the Mona Lisa mine. So once we had those samples, we wanted to answer the question of, is it actually turquoise? And there's a difference between what's called cultural turquoise in the literature and mineralogical turquoise. And archaeologists will use the term cultural turquoise sometimes, and it's basically referring to any blue-green opaque stone that they find in some burial site. They don't actually do much testing on it. They'll classify that as cultural turquoise. And I wanted to look at, well, is it actually the mineral turquoise? So we had to do some more advanced testing on that material. And that included Raman spectroscopy, X-ray diffraction, and geochemistry. And let's get into some of the results from those now. Well, okay, first let's go to, I'll just introduce the background of how I understand the mineralogy of turquoise. So turquoise, as Jacob mentioned, is a copper aluminum phosphate, a hydrated copper aluminum phosphate mineral. And it's the naming member of the turquoise group. And the turquoise group are a few minerals, turquoise, planarite, chalcosiderite, faustite, and hyalite, that have the same structure, but have different chemistry. So they're related to each other mineralogically. And the elements within the turquoise, or within the turquoise group minerals, fit together kind of in a pattern that's shown there in the image. The copper from the turquoise, for example, would fit in where that X site is in this image, and the aluminum in the M sites, for example. And within the turquoise group, there's a lot of substitution between those individual elements. For example, you could have some copper and some zinc, and that would be a solid solution relationship between faustite and turquoise. Or you could have iron replacing aluminum, which would give you the mineral chalcosiderite, or a vacancy instead of copper, which would give you planarite. So we wanted to determine, well, is this planarite or is it turquoise? Because that was the big question that the Arkansas geologists had here. And first, let's take a look at the Raman spectra comparing a Mona Lisa sample to a turquoise reference. It does match very well. There are some differences in the intensity and peak positions, but in general, this matches our turquoise reference. And what Raman spectroscopy is we're basically directing laser light onto the sample and then measuring the molecular vibrations within that sample, which give a signature based on their arrangement and the type of atoms that they are. So that's how we are comparing this Mona Lisa sample to a turquoise reference. We also took a look at the matrix materials to see what minerals we could identify in the matrix itself. And then we also did X-ray diffraction. I think there's an explanation of X-ray diffraction on the poster upstairs as well from Lishua, I think, had the poster upstairs. where they did some X-ray diffraction work, where basically you're directing X-rays at either a powdered or slab sample at various angles, and depending on the crystal structure of the material, those X-rays will diffract in different ways, and so each crystal structure and each mineral will have a unique pattern. And we see again that our peaks match up very well with the turquoise reference. But when we were looking just at the material that we thought was turquoise, we also found that there was planarite and there was faustite using these techniques. So we identified 3 different turquoise group minerals, so it's not all just turquoise at this location. And then looking at the matrix, so looking at that novaculite matrix, we found crandallite, which is a calcium aluminum phosphate, quartz, a lot of clay minerals, accessory anatase, and some iron and manganese oxides that had formed there in a secondary environment as well. And then we wanted to look, so we looked kind of at the crystal structure there with Raman spectroscopy and X-ray diffraction. So now we want to look at the chemistry of the material. So now that we know what its structure is, what atoms are in that structure. And we wanted to, we did a couple of different analyses because we wanted to look at the major elements like copper, zinc, and iron. And we also wanted to look at trace elements. So those required slightly different techniques. All this geochemical work was done at the University of Arkansas Radiogenic Isotope Laboratory, where you're all masked up because you can't have any external contamination of lead or anything that might be on your clothes and things like that. And we're basically digesting and dissolving that turquoise, or at least small amounts of the turquoise, in different acids, so that we could then measure it as a fluid using a quadrupole mass spectrometer. And what we found is that there's really variable amounts of those major elements. So we got copper from barely any up to almost 6 weight percent in what we found. From zinc, from barely any to a major component, and from iron, really variable amounts of iron as well. So that could also suggest substitution between turquoise and chalcosiderite at this location. I've then compared our results, which are in white here, to the results of the only other geochemical study of Mona Lisa turquoise that I know of that's been published. That was done by Stephen Laney at Tards Minerals in California, and he used an electron microprobe method, so a different method, but he looked at old stock Mona Lisa material that he had back from the 80s and 90s. And we get similar results here, although it is difficult to compare 2 different methods to each other. And one interesting thing is that there are no samples, and I know that the Smithsonian has also tested some of these samples. There are no samples that have an ideal copper content for turquoise, because the ideal copper content would be, it's thought of to be close to 10 weight percent, and none of these come higher than 7, for example. So there's some substitution, some vacancies going on in the material, but turquoise is a major elemental component, so it would be considered the predominant mineral species that's located at this site, that it is the turquoise, that is that blue-green material. Now, the standardization for that is difficult because it's tough to say, well, something is ideal or it's not ideal. You got that everything's in between. And so since everything's in between, I think this falls well in the range of what we consider mineralogical turquoise. And then we did different dilutions to measure the concentrations of 2 different trace elements, lead and strontium, in the turquoise, because we wanted to figure out if there was enough in there to do any isotope work. And that's what I'll get to now. An isotope, apart from being a minor league baseball team, also is a chemical term. Isotope would have the same number of protons and electrons as an element, but has a different number of neutrons, and therefore it has a different atomic mass and can be separated by a very highly tuned and precise mass spectrometer. And isotopes can be stable or unstable, and by unstable we mean radioactive. Now both strontium and lead, those 2 elements, have multiple stable isotopes that occur naturally, and so we can look at the ratios between them to understand the history of our sample a little bit better, and particularly to track the geologic processes that might have created turquoise at this location. So let's take a look at the strontium isotope ratios first. There's not that much that can be drawn from these by themselves. The Mona Lisa values are plotted at the top there, highlighted in blue, and we can compare that with the host rock, which were measured at the same laboratory using the same techniques at the bottom, the upper and lower novaculae. You see that it does match up really well with the host rock, having the same strontium isotopic ratios as the turquoise. Now, we also referenced another study to kind of compare our results to see where they stood, and that study was by Alison Thibodeau and Joaquin Ruiz at the University of Arizona, and they measured a bunch of strontium and lead isotope ratios from different localities in the United States and mapped and kind of separated them into regions or provinces. And I've compared our data with their data as well, and we get considerable overlap in regards to the strontium isotope ratio. So you wouldn't be able to look at a strontium isotope ratio and come anywhere close to saying, oh well, it's not turquoise from the Mojave Basin, or it's not turquoise from Arizona, or anything like that. Now, lead isotope ratios are a little more complicated because we're actually dealing with 4 different isotopes of lead. There's lead 204, which is stable. It does not come from any radioactive process. Lead 206, which forms from the decay of uranium-238. Lead 207 from the decay of uranium-235, and lead 208, which forms from the decay of thorium-232. And we can measure the ratios between all of these isotopes to track geologic processes. And specifically, this is used a lot in ore geology when people are looking at where metals are coming from. So by tracking where the lead might have come from, by seeing where lead isotopes might match with a source, since lead and other metals behave similarly in geochemical solutions, we can use it kind of as a proxy for tracking precious metals. And in this example, I wanted to use it to try and track where that copper might be coming from, because there's no obvious copper source. Now, it requires a really precise instrument to do this, and this multi-collector mass spectrometer here was set up specifically for lead isotopes by Dr. John Samuelson of the Arkansas Archaeological Survey, where he actually looks at lead isotopes in the teeth of mammals. And so it's really specified for low lead materials to find lead isotope ratios. So because we had that instrument at Arkansas, I was able to do this study and see what it might tell us about where that copper could be coming from. So here's our first diagram, and I'll try and just walk through this pretty slowly here. On the y-axis, we have lead 208 versus lead 204. On the x-axis, we have lead 206 versus lead 204. Simply because we have that lead 208, which forms from the decay of thorium, we call this a thorogenic diagram. And it's typically one of the diagrams that's used in those ore geology studies. And I first wanted to look at the deposits that do produce copper-bearing minerals in Arkansas. And those are called Mississippi Valley type deposits. In northern Arkansas, there's lead and zinc, which have been mined economically, with some copper-bearing minerals there as well. And I thought, well, it might make sense that the closest potential copper source might be our answer here. And what we find is that those deposits, which all this data was collected using the same techniques at the same laboratory, have a completely different trend and have completely different ratios when compared to Mona Lisa turquoise, which here is those blue circles. And in fact, the blue circles match well with the diamonds on this diagram, and those diamonds are the Arkansas novaculite, which are the direct host rock, which has barely any lead, but still more lead than the turquoise. And if we look at another diagram, where we're now looking at, we're just changing the y-axis here. We're now looking at 207 versus 204 instead of 208. and because it's 207 now, that's from the decay of uranium-235, which gives us a uranogenic diagram, is what it's called. And we're still comparing those same sources here. And we see that Mona Lisa still doesn't match up with any other source rock that has been cataloged by that laboratory. And we also see that it follows, the data for the Mona Lisa turquoise follows a linear trend. And that can actually mean one of two things in lead isotope geology. It can be used sometimes as what's called a pseudo-isochron to determine the age of the lead. So by measuring that slope of the line, sometimes you can get a relative age of the lead. So I tried that, and it gave an age for the lead as being in the future. And so unless we're able to measure lead in the lab today, that hasn't come into existence yet. I mean, I'm not an expert on the time-space continuum, but I had difficulty making that make sense in my head. So our other option for what a linear trend might mean would be two n-member sources, two different sources which have been mixed with each other, and that creates that linear pattern. So you would have one near the top of that trend, one near the bottom, and then because of that mixing, you get this linear trend between those two sources. So we likely have at least two sources for the lead that's in Mona Lisa turquoise. What we also see is that the novaculite itself has a linear trend, and it follows the Mona Lisa turquoise as well. And it's really difficult to separate, to see any difference between the lead in the turquoise versus the lead in the novaculite. So is it possible that all the lead in the turquoise which is not much, is coming from the novaculite itself? But the novaculite has nowhere near enough copper to produce turquoise. So maybe there's some sort of copper source that then is also low in lead, because it's not affecting the lead isotope signature here. And now I've compared our data to some of the data, again, from that study by Allison Thibodeau and Joaquin Ruiz at the University of Arizona, to see how it would compare with their data. And I know that study will be addressed tomorrow at some point, and I haven't spoken with them particularly about their results. But and we use similar methods, but in a different laboratory with a different instrument. But if you were to take their methods and their conclusions about separating certain turquoise mines by, or turquoise producing areas by the lead isotope ratios, the Mona Lisa material would fall in kind of a discrete field compared to a lot of their sites. And I didn't include all of those provinces here because they really overlap with each other quite a bit, just a few of the discrete ones. Now, in terms of using lead isotopes to determine turquoise origin, there are several obstacles to that. One just being the sample prep. So in our case, we took about 250 milligrams of each sample and dissolved it, and digested it. And so it's a destructive technique. Now with practice, we could probably get that down to about 100 milligrams per sample, but you're still dissolving some of that turquoise in acid. And then it also takes a long time to set up the whole process. Takes many weeks of staying in the lab, running all these dilutions and acid digestions. So it couldn't be done in a short amount of time. And also, there's no data on lead isotopes from some major sources in the world. Like this study that they didn't include every mine in North America, and of course, I don't know of any values of lead isotopes from any turquoise in China or Iran or those areas, which obviously would need to be addressed if it were to be turned towards an origin type study in a gemological sense. So just to wrap up the scientific portion of my presentation, so the Mona Lisa mine is a unique turquoise occurrence in Arkansas, but I put that asterisk next to the turquoise because it's not ideal turquoise, but it's there any ideal turquoise out there? Some would say that Sleeping Beauty is close. Some people have measured it as close to that, but it's difficult you can't disqualify this as turquoise just because it doesn't have exactly the right amount of copper in its crystal structure. The turquoise at this location is concentrating along fractures in Arkansas novaculite, which is the host rock. Now the lead isotope ratios, when compared with what the other study showed, do appear to differ between different American turquoise deposits. And the big question remains of what that copper source is, because the lead isotopes, we tried it, and it didn't give us a clear answer as to where that copper might be coming from. And so there are a couple of different options. First of all, there have been localized reports of chalcopyrite being found in the Ouachita Mountains. I haven't found any myself, and a lot of those are in studies where people were trying to get investors to support their mining efforts. So it would be helpful for them to say that there were these indicator minerals that might contain those precious metals. And the other option would be not specifically a copper ore, but a manganese ore. Because in that area of Polk County, there is manganese mineralization around the same elevation along similar ridges that has been mined economically. And they've done some geochemistry on those manganese ores and found that some of them have significant amounts of copper. So if you had a primary manganese deposit, which was then weathered, you weathered that manganese ore, you release the manganese, and you would release the copper that would be there. And so that, I think, is the most likely hypothesis for how how there could be copper to form turquoise at this location. And then there's also implications archaeologically, because according to the people I've talked to at the Arkansas Archaeological Survey, there's no records of Native Americans ever using turquoise from Arkansas. There's no evidence of that site being mined in prehistoric times or anything like that, even though the Caddo tribe has been there for centuries. So it would be interesting to look further into that and see if any of the turquoise that has been found with those Native Americans at their burial sites and things like that, which some have attributed to southwestern sources through trade networks, to see if any of that stuff actually came from Arkansas. And as to whether there are more mines in Arkansas that could be found, or more turquoise deposits, I would say it's likely that small amounts of turquoise are hiding out somewhere. I'd say it's unlikely because there's still no major copper source. It's unlikely there's another economic or commercial turquoise mine that would be found in the Ouachita Mountains. All right, and lastly, I'll just go through kind of what's going on at the mine currently, at least as I understand it. So mining is kind of sporadic depending on, how far along they are with their quartz mines and things like that, what equipment is available. But they'll send in an excavator which removes any overburden that's there, or will widen and deepen the trench. Then they'll send in their miners who are specialized in quartz mining, but they also do this turquoise mining. They go in with hand tools to extract as much turquoise as they can. They then transport that material to the warehouse, which is relatively close by, and then it's sorted by grade. So, a small amount of the material is gem quality to where it would not have to be treated. The majority of the material is too chalky. The majority of the material is stabilized. It's stabilized locally. They tried sending it to China at some point and weren't pleased with the results. So now it's all stabilized by a local lapidurist in Hot Springs, Arkansas. Here's an example necklace here. This is a natural Mona Lisa material here. The largest bead is 35 millimeters in this image, so that's quite a chunky necklace, at least I thought so. And then once that material is either cut or stabilized and cut, it's then sold to certain dealers in northwest Arkansas who have connections with the mine owner, and also some of the material is sold in live sales on social media. So specifically, I think Avant mostly uses Instagram for their live sales. And whenever I've checked them out, there are thousands of dollars that are moving around very quickly And most of it's in quartz, but they also sell a couple pieces of turquoise pretty much each week on average. And they still have a lot of what considered old stock material in their warehouse, so they haven't been doing a ton of aggressive mining. They've been kind of relying on a lot of the older material recently. And the last estimate that I got was that about $20,000 to $30,000 worth of the finished pieces are sold each month by Arkansas dealers, was the most recent estimate I got. And a lot of those pieces are sent from Arkansas to the Southwest to be cut and put into jewelry in Southwestern styles, and then back to Arkansas to be sold. And here are just some more pictures of some of the material that was on the market recently from the Mona Lisa mine. They consider this old stock material from the Mona Lisa. It has this nicer, a greener color to it, and that's, I can tell you there's lots of old stock material that's blue as well, but what they were calling this greener material, the old stock, in one of their sales recently. Right, so with that, I'd be happy to answer any questions that you might have, or I'd be open to hearing what people might think about the largest American turquoise nugget, for sure. So thanks a lot. Yes, go down.
What's the elevation?
It is at 1,400 feet, so not that high.
Not that high.
Yeah, and the highest point in Arkansas is Mount Magazine, and I believe that's about 2,700 feet. So it's, the Ouachita Mountains, those ridges are generally at around 1,400 feet. I think the tallest mountain in the Ouachita is just over 2,000 feet. So it's been around a long time. It's been weathered, been eroded down for quite a while. And they're all sedimentary rocks as well, so they weather more quickly than hard rocks. Yes?
Do you think it wasn't turquoise jewelry by the Native Americans wasn't made earlier because it wasn't accessible? It didn't come to the surface until this first mining event?
Yeah, so the Caddo tribe who were in that area are currently have moved more south. So I think when the mine was first being mined on record that we have, they weren't actually in that area. And I don't think that they were involved by the mine owners at the time. I think they were just trying to sell the material however they could, whether it's as Arkansas or saying that it's Southwestern turquoise. Yeah, but I think there's definitely a possibility that even maybe small amounts of turquoise from Arkansas were used by the Caddo tribe, because we see turquoise in a lot of their burial sites and things like that. And it's quite a ways away from where we traditionally think of turquoise coming from. Yes?
How unusual is it to find quartz and turquoise in the same mine?
So so quartz and turquoise occur pretty often at the same mine. Any sort of turquoise in like sandstones, most of the sandstones we think of have a high quartz component. Now, actually, crystalline quartz is not that common, to my understanding, and you do get a few nice crystals of quartz at the Mona Lisa mine. They're all really small, so they're not really worth mining when there's way bigger locations in that area. But you do get some nice crystals of quartz at the Mona Lisa mine, and really that whole area is just riddled with these veins cutting through everything where those silica-rich fluids were transported. And sometimes there is a lot of room for big quartz crystals to grow. So some of the veins will have a quartz core, and then basically on the outer edges you see phosphate starting to mineralize. And typically it's really small amounts, but you see some of the white chalky turquoise there around the edges, or you might see a small band of blue-green along those quartz veins. But those smaller veins typically aren't of high quality quartz. And in Arkansas, the way that they distinguish the quality of their quartz is by basically how nice the terminations of the crystal are and how clear it is. So if you're looking for the really big, beautiful crystals that are just like looking through water, you won't find those at the Mona Lisa mine, but you can find them in the area.
I'm a geek, sorry. How much did they charge the guys for the fee to go mining, do you know?
Yeah, I actually think the mining company did not charge the YouTuber to take those guys out, because it would then be, a video that gets
Advertising.
millions and millions of views to generate exposure. The subscribers and fans of the YouTuber to come dig with him, I believe the fee was $50 per person. In general, most of them, either if they had a four-wheel drive vehicle, they would take their own vehicle and it was a long train of probably like 20, 25 trucks that were all making their way up this mine road that luckily had been graded, but it was still kind of precarious. But they paid about $50. Also to get those invitations initially, I think they have to be in his premium subscriber club on Facebook or something, which is like a couple dollars a month as well. So that was how that had worked. I think I would say probably $25 to $50 would be what you'd be looking at if you wanted to go individually to that site to just pick through the tailings. And I think it's depending on you could definitely find enough material there to be worth more than that, but you'd have a lot of small pieces, and then you have to figure out how to market those individually. You wouldn't find any real nice turquoise at this point.
How much are these pieces here, how much are they charging per carat?
So I'm not sure what they charge exactly per carat. I think it's I don't know.
That's fine.
I
I would guess from the sizes, I can't tell the sizes, but I was guessing somewhere around $10 a carat, but
okay.
that's just my assumption.
Yeah, I have several pieces that I was planning on bringing, and then they're just left in the trunk of my car in California. But yeah, and
I'll have the same problem tomorrow night.
But yeah, there's a wide range. I think the necklace was being sold. That was being marketed around 5,000, and the biggest bead there is 35 millimeters in diameter. When I compare the prices that I see in the warehouse there with the material that I see in Tucson, it seems quite cheap compared to southwestern localities in terms of the size of material that you get. Now, of course, that's mostly looking at stabilized stuff. I didn't get to destroy much of their nice pieces that were big and natural. Right. Anything else? Right. Thank you all for being here and letting me speak for a while.
Thank you.
Not falling asleep.
Thank you. That was very
Can I take a photo of you pretending to give your talk?
Oh yeah.
Yeah, that's good, yeah.
Oh. I can't open my mouth.
He's done this before. Let's not get too California. That's one of the surfer guys.
He had long hair before he came up to California, so
I know.
it's not something that.
I mean, what happens when southwestern people would meet surfer? You know what I'm saying?
And,
Him, right?
Yeah. Have you picked up surfing, Alex?
No, not yet. All the surfers know Waco though, because Waco's got like
It's
its
got the
own,
surf
like,
park.
It's a surf park, and
There are
apparently it's
professional
famous.
surfers who come to Waco.
Oh, really?
Really?
And what was funny,
Like year round, so.
yeah, my Uber driver when I was there, from Brazil, loves to surf. Said, "You're from Waco? How's the surf park? I've heard about it." I'm like, "Our surf park?"
That's wild, that's crazy.
That's right.
It's like one of those places that produces the waves. And they
Yeah,
can
it
do
creates
that.
its own wave. And
Interesting.
I don't know how big, I've never been there. But the water, I think, is much colder in the Pacific than it would be in Waco, Texas.
The water's colder in the Pacific than it would be in January in Waco.
Anywhere.
Is that their laptop? Or did you
I'll
bring your
tell you.
laptop? Okay, so you just bring
I've been
a
out-
thumbstick?
I've been out in a couple of surf breaks in California and everything.
Yeah.
Yeah, I
It was
just.
brutal.
I was surprised to see everyone in wetsuits. I've never spent a whole lot of time. There's no one without a wetsuit.
I was in like a 3/4 and I was wishing for an immersion suit. I'm too much southern.
He's great, yeah. Yeah. And he likes what he does. This is fantastic. Good job. No doubt. Oh, yeah.
Very, very happy, right?
So too, yeah.
Were the miners very happy with the news?
Yeah, no, they were great actually.
Put it out there, publish it, whatever you need to do.
Yeah, they had.
Except the copper question,
Yeah,
question mark.
that's definitely, yeah, I mean, he had previously sent them some material to the Smithsonian as well to see what they thought about it.
Oh, what did they-
Yeah,
what was
I'm
their-
very reached really soon.
Similar, whatever they said, yes, you get the stamp of approval.
Yeah,
Because I'm sure.
But the difficulty is like, how much.
Now you're a turquoise expert.
Well,
There's no standard for right? Because it has been for there is no real standard
I am going to.
of that, so.
It's kind of like, it's
I was
kind of
joking, I
like.
was gonna put it in my office. You know, we're.
I'd say from yeah. That's right. Yeah.
I got the 101 down.
So, you know,
Exactly. Throw out some of those words. Stabilize. Yeah, all these words. What do you guys have back?
I did get that tonight. They were so good. So, you know, once you get into that world, that's a world, you know, so it's, you know, there's a world, you know, better and worse places I've never been or experienced, but still, that's a world that
Yeah. Well, it sounds like it's been a nice trip so far. Yeah, Sunday I'll fly back, so hopefully everything works out. Because I just decided to go here in this case, late as I said, I'll fly back.
you know, if it's that
There's
important,
only,
you know,
latest
it's
late.
it wouldn't have to go to me. Right, so it's kind of like,
I'll go to Dallas and then,
right.
no direct way the other way.
That's really fun and interesting.
And that's the main thing, and I told my work, I said, hey, I'll let you know, anything that's in Dallas. Well, that's just it. I'll let them over and everything, and then we go in something.
Well, in the planes, I guess they're flying.
There's all sorts of impacts where it's rippling. Well, my daughter was to do a big
Oh,
minor
is Jay
warning
considered a
about
gem?
air.
And that doesn't
But the mineral itself is much harder.
Oh, okay.
He's like, it doesn't get that.
Okay.
Yeah.
I was just.
Is it yellow stone?
Oh, Jasper, okay. So Jasper is like,
Oh, I'm Jasper J, sorry. J. That's not a gem.
I mean, Jasper.
Can it be a gemstone?
Yeah. So my wife got her PhD.
Yeah, there's lots.
So you're out.